Hello everyone. Today we're going to be looking at polynomials and how we're going to be simplifying and multiplying polynomials. Um, how are we going to simplify the polynomial expressions, and how will we find a polynomial model that represents a geometric figure? So first off, what is a polynomial? Polynomial is a monomial, or a sum or difference of monomials. So what we mean, monomial, we often just use the word term. So like if you have a quadratic, x squared plus x plus 1, each element within that, x squared and the x and the 1, can fall into the category of a monomial. And this gets a little bit tricky, but it makes a little bit sense more when we talk about things that happen in the future. That a monomial is a type of polynomial, even though there's only one, and we're used to poly meaning multiple or many. Each monomial in a polynomial is a term, so you've heard me talk about the linear term or the quadratic term and things in previous videos if you have watched my prior videos up to this point. So we're just talking about each piece. What makes a polynomial? No variables in the denominators or in the exponents. If they're in the denominator, then that's a rational function, which we will get into later. If they are in the exponent, that is an exponential function. No roots, no absolute value of variables. If we have a root or absolute value, then we don't have what would be a pure polynomial. Instead, we would have a composition of functions that we would have to deal with, which have an entirely different set of rules. All variables have whole number exponents. If they don't, then we get into talking about things potentially like power functions. We can actually, if we have negative number exponents, then we can actually go back to where the variables are in the denominator and talk about rationals, lots of different things. So what we are talking about is positive counting numbers. So, 1, 2, 3, 4. We can have power 0 in a polynomial, but power 0 just means a constant. So we're going to first look at multiplying polynomials together. When we multiply polynomials together, we're going to use the distributive property, which just means that for whatever you're multiplying across, that you take each term in one of the product factors, and you multiply that across every single term in the other product factor. And then once you do that with one term, you're going to go back, you're going to do it again with other terms. So, and that's just distribution. It's just kind of a repeated distribution process. When you're multiplying two binomials together, we can use the FOIL method, just like you would in a standard quadratic. When you were working with quadratics, you've actually been doing polynomial multiplication since Math 2, Math 1. And it's just we didn't call it polynomial multiplication during that time. However, the FOIL method does not work like in the case above if you have anything beyond two binomials. So be cautious in using the FOIL method, and it will not work as in this case that I've just highlighted here. When we're multiplying a monomial and a polynomial, that is just distribution, as you can see in examples A and B. We're just multiplying each one. This is 4y squared times the y squared, and then 4y squared times the 3, and then you're going to simplify where you can. This example here, this is just multiplying two functions together. These are two separate monomials in this case, but this would not qualify, technically speaking, as a polynomial because the exponents here are -2's. And you can see in this case we have an end result where a variable is in the denominator, and so this falls into a different category all in its own. What if we're expanding the power of a binomial? So whenever you are multiplying something to a and you have a power involved. So my advice to you is to do as is. A plus 2b cubed is just a plus 2b times a plus 2b plus a times 2b. Go ahead and write them out, and then you can pick how you're going to multiply, how you're going to distribute. If in this case, I tend to kind of agree with this particular set, and I multiply the back two polynomials together because just typically you see the smaller polynomial component, in this case a binomial, in front and then the larger one behind. But it's totally up to you. But the key thing to take away from here is that you're going to multiply one piece together. Two pieces together to create one, and then once you get that, then you're going to multiply again. And so this was actually a two-step process, and you can see here multiplying the a, multiply a across all three terms in this trinomial, which is represented here, and then multiply the 2b across all three terms in the trinomial, which is represented here. After you complete the multiplication, which is this row right here, then you look for any kind of like terms that you can combine. So there's a 4a squared b and a 2a squared b. That's going to give you your 6. And then 4ab squared and 8ab squared. That's going to give you your 12ab. And then this would be your final answer. I'm going to switch over into another method here for just a moment, and then also show you how you can verify some of this in Desmos, but you can only do this when you have one variable. So the Desmos tool that I'm about to show you would not work for this problem unless you pull in some other technique. So I will switch over to those videos now. So what I'm going to do now is I'm going to show you an alternate way to use the distribution property in order to multiply your binomials, or sorry, your polynomials together. And it could be binomials, it could be trinomials, it could be anything. And this method takes a little bit more time in the setup, but I find it visually a lot easier to grasp. And so what I have here is I have two polynomials. This is x squared plus 3x minus 1 times 3x squared minus 5x minus 2. And when I do this in Desmos, you'll see how this looks. And so this method is called the box method because we're going to divide our polynomials up into rows and columns. And then what happens is, so you can choose, it doesn't matter which one that you pick to go from as represented in a row versus in a column. You can pick either one. But then when you draw out your grid, what you have is a one-to-one correspondence of the product that's going on. So in this first cell here, this is x squared times 3x squared, and you can pick any cell. This cell that I'm at down here is going to be, it's in the 3x column and it's in the minus 2 row. So I'm going to multiply those two numbers together. And so as you do this, so I'm just going to start here at the top. This cell right here is x squared times 3x squared, which is going to be 3x to the 4th. And then I'm just going to work my way across in rows. You can do this however you want. I tend to work with rows. So this is 3x squared times 3x, so that's going to be 9x cubed. And 3x squared times negative 1, which is minus 3x squared. And as we continue to do this in the rest of the columns, rest of the rows, rest of the columns, then you fill in this nice little box that we have here. And there are multiple advantages to this. For one, if you set this up and if you have no missing terms, then what you get is a nice diagonal relationship. If you look at the diagonals, you see that, so I have x to the 4th, then I have the cubes kind of in this diagonal, I have the squares in this diagonal, the linear terms in this diagonal, and then my constants in that last cell. So it's going to make things very easy for me to write out and combine it, and as I continue solving the problem. If you had something like a 0, term, so I'm going to change the problem at this point. So what I have here is what I'm going to continue on with in the next problem. So you can write this next part down or not, but what if instead of having x squared plus 3x minus 1, what if all I had was x squared minus 1? And so there's no linear term. Well, if I just put in a 0 for that linear term, all of these values would become 0, and you can see that the diagonal property would actually still hold. If I eliminated this column, let me see if it'll let me do that. It doesn't hurt anything, but you can see I don't have that nice diagonal correspondence. So you can still do this whether you have missing terms or not. You can add in the missing terms as 0 quantities. It really doesn't matter. And it's okay. So I'm picking up with the same problem before I started taking away some of the terms. So this right here is going to be the original problem. And what it does is it generates a graph. And when it comes to polynomials, there are definitely pieces of information that we can pull from the graph. There's a lot of different things that we can determine about a polynomial just by looking at the graph, and they can help guide us towards the answers. But when it comes to me multiplying these together, I'm not quite concerned about how the graph looks specifically, as I am just a couple of general trends. So at this part, this is the original problem. Always graph your original problem. And you can do this with most any kind of math problem, especially in the algebra. And so the technique that I'm showing you now is to graph everything one step at a time. One step at a time. Because if you wait till you get to your final answer, you can always check and compare the graphs. But if you make a mistake, you don't know where you made that mistake. So as you work this, so here's my original problem. I used the box method, and I've gotten all of these values now. I'm going to graph it, and what I see is that the graph overlaps my original perfectly. And so that tells me that everything that I did in this step was correct. Let's say that I accidentally made a minus where I should have had a plus. I see that these graphs don't match. And so as soon as those graphs don't match, that tells me something about this isn't right. The other thing that I can do to kind of help me visualize what's going on a little bit better, I'm going to go up to this gear. And when I click it, I'm going to go and select either one of the equations. It really doesn't matter. And for style, I want to change this over into dots. And so now that helps me see that things overlay properly. I've written this out in descending powers. And so now we start combining the like terms. So here is 3x to the fourth. There's no other x to the fourth terms. Now I have x cubed and x cubed. So I'm going to take positive 9 and I'm going to subtract 5. And so when I do that, 9 minus 5, that's plus 4. I have negative, here I have negative 3 minus 15, so that's going to be negative 18. And then I have negative 18 minus 2, so that's going to be a negative 20. So this is negative 20x squared. And every time that I'm doing this, I'm glancing back over to make sure that my graph still aligns. I'm going to intentionally make a mistake here, so I want you to watch. So 5 minus 6, that's going to be a negative 1, but let's assume for a second that I was in a hurry, I rush, and I do plus 1. It's kind of hard to see, but these dots are no longer matching. So I go back, what did I do wrong? I look at my original work, and then it's the minus. Okay, now everything works. And this is now my final polynomial. And so that's going to be my final answer. And then from this, if there were other questions like what are the roots or zeros, can this be factored, is a prime, I can then take this information and then work with it a little bit further. So I hope this helps you in being able to not only multiplying polynomials together using either just the standard distribution. There's also vertical multiplication techniques, and as in addition to the box method that you may like, and but then also just how to help check to make sure your answer is right. Because I know for me, when I was first learning how to do this, I understood the process pretty well, but you kind of get to the end of it and and just by looking at the numbers alone, it's hard to tell whether you're right or wrong. So I hope all of this helps. Okay, so now we're going to take a look at a couple of just practice problems, and we're going to, I also want to look at just a slightly different representation. So we're trying to find the area of a rectangle, which is length times width, and we're given these two binomials, 7 plus x and 2 plus x, which alternatively we could have written as x plus 7 and x plus 2. Going through the distribution process, we arrive at this final answer of x squared plus 14. And one of the things that I want to bring up with this is, even as a mathematician, when I just look at this number, that can be meaningless outside of the context. And honestly, if I were working with this problem, I would actually look at it in this term, in the factored form, rather than the quadratic, because what's changing? Well, I'm changing the length. I'm changing the length and the width by the same amount whenever I change x. Sometimes, I think to really see what's going on, it helps to look at a different representation. And so you can see here how we have this rectangle that we're trying to find the area of. And so now these numbers hopefully will start to make a little bit more sense. This is the 7 plus x side here. I'm going to call that my width. And I know it doesn't quite match up here, but traditionalist in that the width is the horizontal, and the length is right here. This is the 2 plus x, and as you kind of look at what happens, so if I change this x in the length and this x in the width, they're going to change by the same amount every time. But there's an area here that's represented in the blue that no matter what, it's not going to change, and it's going to be 14 square units, which comes up here because it's 2 times 7. There's also always going to be some square. If you extend this line here in the vertical down to the end of the box, and you extend this line in the horizontal to the end of the box, you'll see, you can envision that there's a square here, and that square is always going to be whatever you choose x to be times whatever you choose x to be. So it's going to be x squared. And you can see that it will form a square no matter what length we choose for x. And then there's also going to be whatever length we choose x times the 2 from the one problem, as well as whatever the length x is times 7. And when you add those two together, if I could physically move these two pieces, I would see that they would total and be 9x. So the formula actually, has a direct geometric representation. It's not always convenient to look at it in these formats, but it's just it's another way to help you see a little bit about what's going on. So now we look at these two problems. Triangle has 3 sides. We have three different lengths, and then we want to know what the perimeter is. Well, you could, if you were given a specific value for x, you could plug that in to each of these 3 equations, find those lengths, and then add those lengths together. But algebraically, we can take these 3 lengths and go ahead and combine them together to form a new single function. This goes back into those function operations. And so then once I decide what length I'm going to choose for my x, I only have to do this one time. Similar idea here. Okay, the dimensions of a window are 3x by 10 and 2x plus 6. I don't know where these numbers came from. I don't know why they fall into these particular constraints, but for now, we just have to operate under that they are. And as we advance in math, we can see why these numbers come up the way that they do a little bit further. But so let's just assume that we are operating under these constraints, and I want to know what the area is. Same thing. I could, once I decide, well, maybe I want my x to be this particular value, let's just say 5. I can say 3 times 5 is 15, plus 10 is 25. 2 plus 5 is 10, plus 6 is 16. And then multiply. And then multiply those two numbers together, 25 times 16. Or I take these two, I know that I take the two factors, I know I'm looking for area, so I multiply them together, and now I get a single formula that I can plug in 5, and I only have to do the computation once, and I'm going to get the exact same number. A rectangular shipping container has a volume of 2,500 centimeters. The container is 4 times as wide as it is deep, and is 5 centimeters longer than its width. So we want to find the equation of the container, which is here. Okay, so we're saying length times width times height. And if we're calling the length x and the width is 4 times as wide, well, okay, so they use the term deep, and and that's just one of those things that you want to be careful of. Is we change terminology because there is no set standard for what term to use. When I talk about a box, I typically will refer to length times width times height, and other people might use the term depth. But for some people, when they're talking about depth, they may be talking about the height. And for visual representations, a lot of times depth means length, but sometimes you might call it width. So you just want to remember there are 3 components that you're multiplying together, and make sure that they are all 3 represented properly. So the container is 2,500 cubic centimeters. This is going to be length times width times height. If I call the depth x, the width is 4 times that amount, and the length. Okay, so we kind of switch these around some, but it's okay either way. So as it turns out, the author used height as depth in this case. The length is 5 centimeters longer, so there's your plus 5, than the width, which is 4 times x. So that's where the 4x plus 5 comes into play. You can multiply all of these together. So x times 4x is the 4x squared here, times this other binomial. You get 16x cubed plus 20x squared. Sorry, I'm just trying to zoom in here. So that's where this particular equation comes from. And then we want to know, okay, well, what are the dimensions of the container? Well, you can graph this, and I will post a picture of what this graph looks like, as well as highlight its intercepts, because and so what I'll explain. Check that. I'm not going to post the picture. I'm actually just going to do a very quick video that explains, where these numbers came from. And when we do, first there's going to be 2 zeros that pop up, and as potential solutions. And I can't have height 0, so that or depth 0. So I can rule those out, and so then what I'm left with is the intercept 5. So if x is 5, which I'll explain this in just a second. If x is 5, then that means that the width is 4 times 5, which is 20, and then the length is 5 more than 20, so where we get 25. So the recommendation here is subtract 2,500 from subtract 2,500 from both sides, and so that's where this equation comes from. And then find your x-intercepts. What I'm going to do in Desmos achieves the same thing, but it's going to be just slightly different. And I'll jump over to that screen now. Okay, so as I had told you before, I was going to show you how to do this in Desmos. The first method that was used was you set everything equal to 0. You subtract 2,500. You subtract 2,500 from the from the right hand side, so that way it's equal to 0, and then we can see the root of 5, 0. And I want to just kind of briefly take a look at some of the different things that are happening here. So let's see here. As I zoom out, okay, I can see, you know, here's this cubic. There's some things that are going on way down there, but ultimately it doesn't really change much about what's going on. The other method that I want to show, because sometimes there's missing information that could be very relevant to the problem, is I want to go back and look at this particular problem. And the thing about it is that this being an equality, we can use that to our advantage. You know, this says that the left-hand side at some point must equal the right. If not, then it's no solution. It's undefined. There's going to be something about it that just does not work. And so what I want to do is I want to actually now, I just want to take a look at what happens when I graph both sides. So this is 16x cubed plus 20x squared. So that is that's my left-hand side, and then I want to graph the right-hand side. Now the thing about Desmos, whenever you do this, is I just put in 2500. That tells the program that it's just a number. If you want it to graph, you have to do y equals. And so let me put this on projector mode so you can see it a little bit better. What I'm looking for now is I'm looking for the intersection of these two lines, this one and this one, which means I need to go to when y is 25, y is 2500. So I'm going to change my window size. I'm going to go a little bit above 2500, just that way I can see, and then there's going to be the answer that I'm looking for, which is 5, which has a direct connection to, let me see this a little bit better. Okay, this 5, from when I look at the intersection of these two equations, and this 5, it's no coincidence that they're the same, because what we're dealing with are equivalent equations in this case. There are mathematical reasons why, when you're trying to solve this by hand, why this is the preferred method. But if you're going for graphical approximations, looking at the intersection point of these two equations also works as well. So always remember that as a potential backup. So here's another example of just utilizing the simplification and being able to come up with a single equation would make things a little bit easier as long as you are operating under the same constraints. We want to find the area of this particular floor plan. Going back into some of your prior math classes of composite figures, if you just, this floor plan can be broken up into 3 rectangles. If you know the area of each of these rectangles and you add those 3 areas up, then you should be able to find the overall area. So we can just take a look at this in terms of its 3 components. So this one, this is a large rectangle here is 4x, and it's times x, the length. So this is 4x times x, which is 4x squared. So that's one of the components. We have this rectangle here, which is whatever x is going to be half and half. So when you multiply those two together, you get x squared divided by 4, or 1/4 x squared. And so then there is that term. And then finally, we have this rectangle, this third region. This is 4x minus 4 times 8. So multiply those together, you get 8x minus 32. And then you look to see if there's anything that you can do to combine and simplify. Well, there's a little kind of issue that I take with this. Technically it works and everything's okay. I would, because what we're doing is we're scaling it by 4. Either way, though, you have the 8x, you have the 32, and these are like terms here, x squared and x squared. So me personally, I would just say 1/4 x squared plus 4x squared. That's either 4.25 x squared or 4 1/4 x squared or 17 over 4x squared, and kind of leave it at that. They scale this because, first of all, this is a scale model, so it's a little bit more okay. And that gets rid of this fraction, and then it becomes a lot easier to see, you know, okay, you just combine these two terms, and that's how they come up with their answer. So these are some problems that you can try on your own. And so if you want to take more time, just please pause the video so that way you can work on these. If you have any questions, feel free to ask your teachers about these later. In the next lesson, we're going to look into what happens when you start dividing polynomials. I will say that lesson will take a little bit more time to kind of sift through all of the information, because as we're going through these, we're just having to get as much information as clear as possible. And when we're talking about division of polynomials, there is a lot of material to digest in that process. So look forward to seeing you next time. Have a good day.